at the Federal University in Itajuba, and he's on a sabbatical, I believe, visiting our institute until July. And he's working on the gravitational problem of two bodies, and he's going to talk about determining the self-force corrections to the equation of the separatrix of a Schwarzschild black hole. So thank you, Ricardo.
Thank you for the nice introduction, Rogério. And I also thank Walter because I was late here. I had some troubles. So thank you for substituting, setting this interchange. Okay, so that's the topic. That's a problem that I've been working on with Ricardo. I proposed in this topic, and we have been fruitful along this line. So the outline of my talk is I briefly review the two-body problem in general relativity and gravitational waves emitted from compact binary coalescences. Okay, then I will make a review of what happens when we study scattering and capture of a probe particle in Schwarzschild. That is important because what I will study later is the same situation, but the particle would no longer be a probe. It's going to be something massive. So as it moves in space-time, it also curves per space-time. So eventually, this new massive particle could eventually be another black hole. So this is what happens in the gravitational waves that we are detecting on Earth, right? So the key point here is the gravitational surf-force. When we study the movement of a probe moving in Schwarzschild, there's no self-force. The self-force arises precisely because the two bodies are moving, the two bodies are curving space-time. Okay, so a key test of any result that we find here is that if we neglect the self-force, we recover everything that is known in textbooks for a probe propagating in Schwarzschild space-time. So then I will see, so when one turns on the gravitational surf-force, the problem is it's quite non-trivial. So there's a model. There's a model here that I will talk about. It's a toy model. It's an interesting toy model, recent, for black hole scattering. When I get there, I'll tell you what's about. So we've done some computations that fit in that model. And the most important thing that they're useful for the GR calculation. And then I have some final remarks. In this part, in these two steps, 4 and 5, I will write some calculations just to give you a flavor about the sort of computations that we do.
So have you final remarks?
Sorry? Yes, yes. Okay.
Well,
I want to stress. Okay. So the two-body problem in general relativity and gravitational waves emitted from compact binary coalescences. Okay, so the main motivation of this is, of course, gravitational waves, right? So if one goes into LIGO homepage and searches there for the sources for the gravitational waves, okay, there's more than one sources. The principal one is the compact binary coalescences, right? That's the only one that so far has been detected, right? But okay, there are plans for the future, LISA detectors in the sky to open up the other frequencies and so on. But up to this moment, what has been detected so far is just the gravitational waves coming from binary systems. So that's the main motivation for this. Okay, so just to give you a flavor of the equations that arise from this problem of the two-body problem in general relativity. We've got Einstein's equations. Okay, so that's the left-hand side, the gravitational field. In the right-hand side is the energy momentum sensor. So we have two bodies spinning around. So first model of this, if you consider them point-like, so they will have some delta function. They will be singular. And okay, this is just a model because it has problems. The problem is that since T mu is singular, uh, metric is not well defined in the places where the point-like particles are staying. So when you go to find the geodesic, to solve the geodesic, it has problems exactly where the probes are moving, right? So but okay, anyway, if you want to smooth this situation, you solve this. But at least if we are very far apart from the binary, this is enough for a first look at the problem. But it's a highly nonlinear problem that cannot be solved exactly. And this is the reason for the different approaches and things that are going on. And this is what has to be done to characterize the gravitational wave. Okay, so as I was saying, if the distances are far away from the distance of the binary characteristic distance, and if the velocities are not so high enough as compared with the velocity of light, okay, if you substitute this perturbation, it is reasonable far away from the compact binaries that spacetimes become almost flat with tiny perturbations, and the equations for these tiny perturbations are linear. That's the thing. So the Einstein's equation become these equations with the two sources. Okay, and this, if one goes on and solve this in a first approximation, the so-called quadruple approximation, one finds this result, right? For the two kind of polarizations, plus and cross, and this is okay. This is a purely sinusoidal description. It requires to be corrected, but it's the first approximation. And this, in principle, leads to that part, the spiral part of the signal from the gravitational waves that we detect here on Earth. So this is a register of the first 6 events of the detected, and so they all have this pattern. And it's a very good confirmation of what's predicted by Einstein theory, right? So this format here is realized in the detections. Okay, so by now we are here at this point in the low frequencies, right? From a few hertz to maybe a kilohertz, something like this. So this at this moment we're in terrestrial. So there's LISA plans for LISA and also for the PTAs, pulsar timing arrays, and that's the plan for the future. But for this moment, we are still here in this side, this spectrum. Okay, so at this point, I will make a review of this interesting subject, which is required for the sort of calculations that I want to show you. But as I told you, this is the part in which space-time is fixed, is constant, and there is a probe. So everything I would be saying at this point is for a probe moving in a fixed space. Okay, so I will be speaking about scattering and also about the capture. So when you have scattering, what is characteristic that you have the probe coming from infinity. It's characterized by so this is the impact parameter comes with some known velocity from infinity, and as it is mentioned there, it will be scattered. And the interesting observable is the scattering angle. Okay, so for example, that trajectory in this case, the center of gravity, it's in the origin. Those two lines are simply the asymptotes and where they intersect, but the center of gravity is there. So one possible trajectory could be something like this, in which the scattering angle is less than pi/2. Okay. This is only to show you that, okay, when one does the calculations in Newtonian gravity versus general relativity, okay, there is some small difference in the beginning, but it depends on the kinematic conditions. So that difference may become huge. But in this case, it's shown there's the gravitational from GR, and that's from Newtonian. It's a big bigger. Okay, so this is another situation that might happen. Okay, this is taken from this reference, and it's a genuine trajectory that can be found solving the geodesic equation, but it's for Schwarzschild. But that sort of movement, in the sense that it passes back from the object and then comes back. The scattering angle is between pi/2 and pi. This also can happen in Newtonian gravity. Of course, the trajectory will not be exactly the same, but this is allowed also in Newtonian gravity. But this sort of situation that happens, it's predicted in general relativity. Okay, the probe comes here almost one turn, and it goes back. So in this case, the scattering angle is a bit less than 3 pi/2, but this is no longer does not happen in Newtonian gravity. So this is a quite different situation. And here's the critical situation in which the probe is captured. Okay, and what it happens, it's an infinite times to get in the black hole. So the scattering angle becomes infinite. This is a result that will arise in the calculation that I will do. Okay, so all this that I will tell you in this section is standard material from general relativity textbooks. Okay, so this will be an overview. That's the Schwarzschild metric. We're working in units where the speed of light is 1. The probe comes from infinity with impact parameter b. It is equivalently described by an energy, relativistic energy, E m over the square root of 1 minus b squared, and also with a relativistic angular momentum. Okay. So solving the equation of motion for the geodesic and so on, there's a sort of energy conservation equation, and then there arises an effective potential, just like when one solves this problem in Newtonian gravity, but this is the case of a Schwarzschild black hole. So that's the expression for the effective potential. It depends on the value of the angular momentum. And from this, this sort of...
Can I ask a
Yes,
question?
please.
So in the energy conservation, do you include the possibility of emission of gravitational waves?
Since this is a probe, there is no emission. That's the reason.
Okay.
Mm-hmm. So this is a sort of diagram that arises here. it's exactly the analog diagram that one sees in Newtonian gravity. What is Newtonian gravity? Okay, in this case, the this is one. This is normalized, right? Oh, so it's divided by m, the mass of the probe. So the shape of this is something like here. Okay, something like this. This is in the case of general relativity. If you compare with the case of Newtonian gravity, it's almost the same in the beginning, but then it goes Newtonian gravity, the shape of the effective potential is just like this, goes out. And in the case of general relativity, the gravitational field is so strong that it makes it down. Okay, so what happens then? For different values of the angular momentum, you have these different curves. Each of those tiny curves is a different value of the angular momentum. For example, the one I've drawn here, it certainly has an angular momentum which is bigger than 4gm. There is a critical curve in which the one shown there, a peculiar value for which it matches the energy equals 1. Energy equals 1, remember that it's energy, the energy over the mass. So energy equals 1 means the energy equals the mass, mc squared. So in that case, it's a particle almost at rest. So the energy is simply the rest energy. In that case, the value found is exactly this one.
So the probe can be massless.
Okay. It's not massless, or it's not massless.
But it could be.
No, because if you
light can also be.
You cannot treat it. It's a separate problem. The no geodesics are not a limit of the situation. So it's not the same problem. So you cannot take the results that one has here and put mass 0 and recover the non-geodesics. Okay, so if the curves that are shown here, for example, here, this one has a L which is lower than 4gm. And all the curves that are above this value of the energy are curves for angular momentum less than this critical value. Okay, so if we give the particle some energy different than 1, the particle comes from infinity. So if this is the situation, and you have an angular momentum which is less than 4gm, it would be swallowed by the black hole, right? There's no chance of crossing the potential at any point, so it will come and will be swallowed by the black hole. So if the angular momentum is less than 4gm, no matter what energy the probe has, it will be certainly swallowed by the black hole. So the interesting situation comes when we consider an angular momentum which is bigger than 4gm. Okay, so
sorry, just an naive question. For the particle to be swallowed by the black hole, is it necessary that the impact parameter must be smaller than the Schwarzschild radius of the black hole?
That's a good point. That would be the first question that I would have asked you. Certainly. So this is the radius is 2gm. So c². That's the Schwarzschild radius, right? For sure, if the impact parameter is of the size of the Schwarzschild plug, it will be solved. But when there's capture, is something more interesting, that it can be, it's bigger than that. Something like this, and it can be solved.
It's not just going in orbit, it's swallowed really, but
From our point of view, an observer at infinity, we will only see that it goes infinity. We will never see it crossing the horizon, right?
But there's no dissipation, right? So it doesn't lose energy. So it should.
In principle, yes, but since it depends on the mass of the probe, it's negligible. It's negligible, right? When we consider a non-negligible mass, it's when the self-force effects will arise. But when you have a probe, it's going to zero, but not zero. So if you compute the radiation, it has a factor m in front, so it's negligible. Okay.
No, I thought it was just go around, because the angular momentum doesn't change. So as you go around, not fall. But
So the addition is full angular can be conserved while the trajectory gets closer and closer to the level, isn't it?
and then the speed of three. Yeah. Okay.
Thank
Yeah.
Okay. Okay, so that's an interesting fact about capture. It's a impact parameter which is bigger than the size of the. So this is certainly something that does not happen in solid gravity, for sure, right? So okay, so that's what I was telling you. It is required that L should be bigger than 4 GM in order to have a chance for scattering. So if it comes with this energy, there's the point. This is the minimum radius, and then goes back. So in that case, there is scattering, right? So as I told you, it's less than 4 GM, it's always captured. Okay, so the interesting situation is that when the angular momentum is bigger than 4 GM, so what is the critical value? It says that there's a critical value for the angular momentum, and it depends on the energy. And it's exactly that situation, although that situation that is it's shown there, it's the one that arises for a particle with minimum energy, but okay, suppose the energy is that one is on red. So you have to look which is the curve which precisely matches there in one point only. So like this. Okay, so if that is the value of the angular momentum for that value of energy, they will meet only at this point. This process will take an infinite amount of time. And this is the critical situation when capture happens. So for a given energy, if the angular momentum is less than that value, it will always be captured. So how to find this mathematical condition? It's as I mentioned here, it should be a maximum. So it's an unstable circular orbit. And also you have to, the value at the maximum should be the value of the energy. So those are the two conditions. Okay, so if you solve these two conditions, you arrive at a expression for the separator, right? So given an energy, right? Given an energy, this gives you the critical value of the angular momentum. Or if you might think of it in terms of the impact parameter, you also have an expression. Okay, it's just a change of variables, but that's the situation. And something interesting that can be seen from that formula is that notice when the speed goes towards the speed of light, tends to 1, if you do the calculation, that's the value. So this means that even if the probe is traveling very, very fast,
Particle is massless.
it's massless.
Now you can get the massless limit.
Okay,
That's
okay, okay. So that's why I put it tends to.
Yeah.
Okay, but the interesting thing here is that maybe traveling very, very fast. At first, one might think that it's so fast that it will ignore the presence of the black hole. But no, what it says, this result, is that there is a critical value, which is that one. So that means that there's always a chance of being captured by the black hole. So even if it's very, very fast, if it's within that critical value, 3 square root of 3 GM, it will be absorbed. It will be captured. Okay. So what about the scattering angle?
So that can be tested by these pictures of the black hole because it has this radius, first radius.
Just have a here.
Sorry, I don't know.
So you have a picture of black hole, right?
Yes.
From the HD, Horizon Telescope, Event Horizon Telescope. So you see the horizon, you see light,
Yeah.
and you see the shadow of the black hole. So there's a radius, a minimum radius. So that's related to this minimum impact parameter probably.
Yes, but that case would be the computation for light, right?
Which means a very fast part.
Okay. Okay. So what about the scattering angle? So
Interrupt just a sec, just to understand the capture effect. So by capturing, you mean actually getting to a bound state, right?
Yes,
You gotta
yes.
enter into the
That-
bubble.
yes,
And so do I get it properly that it takes an infinite amount of time to reach this R because it arrives and then starts, and it remains closer and closer and closer to this final equilibrium point, which is a meta equilibrium point.
Mhm.
And at which point it remains there, but it takes an infinite amount of time anyway.
Yes,
Is that it? Okay.
that's it. Thanks.
It's captures, not being swallowed by the black
Yeah.
hole. Yeah, no, I understand.
Uh-huh.
So the-
And there's no curve, so there's no shape, right?
So, okay, so it one solves the equations, that's expression that can be found for the scattering angle. I missed there is a minus pi in the right hand side. So there is an integral expression and a minus pi. But okay, that's expression. So what could be interest? There's an R minimum, and that R is the lower limit of integration, is exactly one of the roots of this. It's it has 3 roots. It's a cubic equation. It has 3 roots. So it's the largest one, which is positive. Okay. So this sort of integral it's what is called an improper integral because the integrand diverges here in the lower limit of integration, but it's a mild divergence in the sense that when you integrate over it, it still gives a finite result. But I will come back to this in a moment. So for a dimension to the energy E, it happens that the scattering angle diverges if it has this critical value L. And I remind you that that's the expression. So one might think, how do I see this expression for L within this context, right? Let me go back. How can I arrive to an expression for the critical L for a given energy within this context? What happens very quickly is that one can write the one over R1 minus 1 over R. The three roots, one can write this in this, the three roots, right? And you have some positive constant here. The positive constant. So, okay, the critical value, this is what happen when you choose the value, you synchronize the value of the angular momentum and the energy such that two roots here meet, which is exactly what happens when we have this situation. Originally, there are two roots. The third root is a negative one that you cannot see in this diagram, but when you demand that these two roots become one with a double, what do you say, double fold, double fold, okay? That's the condition. And what happens here, it means that you have a repeated root. So the square root of this just is, if I call it something like this, right? And you have an integral over this. So this diverges logarithmically. That would be, okay, that's what I was telling you. So in this diagram, it's a diagram of the scattering angle versus the angular momentum. This is normalized, divided by GM. So in this case, I've chosen the value of energy equals 1, almost at rest. So the divergence happens for this value, J equals 4. So that's J equals 4 there, and you have a vertical asymptote. And so every diagram for the scattering angle has this this shape. So near the separatrix, that's the sort of behavior. It's a logarithmic behavior that can be fine from studying this and that integral, where that is known. Okay, or equivalently, you can write it out in terms of the impact current. Okay, so now going to the gravitational surface. So, okay, so the situation is that the self force is something that also happens in electromagnetism, right? So there are two components that contribute to this self force effect. So one is the dissipative radiation, and other one is a conservative component. The conservative component, the one here, one might think of it as something that keeps the momentum and energy conserved, but it has this, it has this precession effect, but basically it keeps the energy and momentum conserved. And okay, the other one, which is radiative, makes the quickly spiral. That's a qualitative way of differentiating both situations. Okay, so in these computations, in these situations, we'll have a situation, a small number, but which is not zero, which is the mass ratio. Sorry about this. This will be, that is the equation of the geodesic. the left-hand side usually is equal to 0, but now you will have some contribution from the radiative component. I'll speak a bit more later. So a simple example where one can visualize these cell force effects and will be also useful to mention the post-Minkowskian and post-Newtonian expansions is the probe particle in Schwarzschild. So you can do the calculations. When one arrives to is this is the expression for the Hamiltonian. Okay, it even substitutes the Schwarzschild metric. That's the expression where you see there's the Schwarzschild radius RS, which is given by that, and it has this expression. Okay, so there are two possible kind of expansions that you can do when you consider this expression. One is that you consider the velocities very much lower than the speed of light. And the other situation is when the distance is very much far away from the black hole. Okay, so there are independent expansions. So one is called the post-Newtonian. So what happens if one does an expansion in powers of g, which is a small number, right? What one gets, you do that expansion. At first, there is simply the Newtonian description of gravity, and here's the first correction in 1 over c squared. And it's an infinite series in powers of 1 over c squared, right? And okay, that's the result that one gets. But when one solves this problem from the two-body problem in general relativity, it's a calculation that cannot be reproduced 100% by this, because this is space-time which is fixed, right? But the result is that some new terms should be added. And those new terms are precisely the cell force corrections, which take into account that both bodies are massive. So those terms cannot be defined by working with the Hamiltonian of a probe in Schwarzschild. And also, if you do the PM expansion, that would be in powers of g. So what one finds, there's the Newtonian potential, but it is multiplied by relativistic corrections. A characteristic of the PM expansion is that 100% relativistic. You see there the Hamiltonian of a free relativistic particle. So, okay, if one compares with the relativistic expression of the two bodies, it's an expression that like that. That's the expression for sigma. One has to open it and find that there is the self force correction, which is should be exactly this one. And you find there at order g. That should happen, but didn't open that detail. Okay. That parameter, which is called the symmetric mass ratio, is given by that. And it goes from 0 to 1/4. Okay, so summarizing, the cell force effects and the radiative corrections are the results that come from general relativity, but that cannot be found by just studying a probe in a fixed background. So these come from solving the complex problem of the two bodies. Okay, so this is a very much cited diagram when precisely of the different compares the post-Newtonian computations, and here the post-Minkowskian computations. So in principle, what is known here are the non-self force effects, right? as I showed you, go to infinity, but those effects that do not carry the new parameter, those are knowns. So any computation, new computation that gives a new result, it's genuinely something that gives you the new contributions, new squared, new cubic, and so on. So in this diagram, they're not shown, right? The specific self-force computation, but when any of the authors found a new contribution, the new result is precisely the self-force productions. What they do, they find the whole expression, but what is new really there is the self-force contributions. Okay, so now about this toy model about the deflection. Okay, this is a toy model due to Barak and collaborators. Barak is a guy that has been working for more than 2 decades on self-force computations, has many important results, and those were students by that time, Oliver Long and Christopher Whittle. Now they are postdocs somewhere. Notice that the second of these papers speaks about plunge. Plunge is the situation for being captured, and they try to do self-force computations, but it is a model. So I will briefly tell you about this model. Okay, so okay, the volume before we the time and wrong and blue ones. So another hole, which is Schwarzschild under study, and another probe. So here comes the model. Which is a scalar particle of mass m, very much lower than the black hole mass, and which has a scalar charge Q. Then, as I told you, space-time is fixed, just charge you. So this is a limitation, right? Because for the complete two-body problem, space-time is not fixed, it's something that is time-dependent. So this is a simplification that they do when they have the order results. What happens is that as the particle moves, okay, it's accelerated. So now radiates. Now it is massive. So now you take into account this effect. The problem is, so now the problem of the equations in principle should be the one that I showed you in the beginning with the general relative Einstein's equation, with a momentum tensor and so on. That's so complicated that the idea of these authors is to simplify the situation a little bit. So this is radiates, okay? But those are not genuine gravitational waves, are scalar waves. See? Okay.
So that's a simplification.
For sure, it's a simplification.
Sorry, what is it you mean explicitly by scalar charge and scalar waves? What is the coupling? What is the underlying theory for these particles?
Yes. Okay. Now I put the equations. Okay. So it's basically it's the Klein-Gordon, massless Klein-Gordon equation for the scalar field. And here it's the source. So it's a charge, current charge particle. So here you have some delta x. Here's the trajectory. So this is the tau divided by where it. This is as far as the description for the phi field. And first, and the other equation, you have the equation for the geodesic that may be written here in beta is the for velocity. So usually this is 0, but this is now the place where the cell force. And so the expression for the cell force, you know the charge. Okay, this is a problem that has been studied in 2002 by you authors. Tyler and Wilton. So that's the description. Okay, so you see, this would be the analog, the simplified analog of this equation, right? You have the G Newton over square some factor, and he give the energy momentum tensor, right? Remind you that the energy momentum tensor that I showed you in the beginning for point-like particles is something like this. And this other equation is the part of the geodesic. In our case, in general relativity, there's no cell force, okay, so that's the situation. But okay, that's the model. So they are interacting, right? So the picture is that space-time is fixed, and this irradiates its scalar field, which is being forced by the particle, which has this scalar charge. If this scalar charge is 0, so the equation would be for this Klein-Gordon from 0, and since the infinity is 0, it will give a contribution. And so when you turn on the charge, this sources the field. Okay, and on the other side, so this is the modification of the geodesic by the. So this is the model, right? I just want to concentrate on what I can take from this for my interest, which is the study of the separatrix, how this is affected, and they have results for this. So a parameter that arises in the computations is the ratio of Q squared and the product of masses. And this parameter, they deal with it as being very, very much smaller than 1. If you think of the gravitational case, this would be something that contains the gravitational constant G, that it is contained something small. So this would be mimic the situation. So they have many results. What they do in their work, they have some analytical computations, but some numerical computations and strongly numerical computations. So it's even if this is simpler than the original gravitational problems, it is hard to solve. So it is required numerical things. So
Ricardo,
Yeah.
just to say that you have like 10 minutes, okay?
just that.
Yeah, something like that.
So let me see how. Okay, so I better.
Better hurry.
You should have told me before. Since you told me only now,
No, but this is, we have to have lunch, right?
well, you can have it here. I don't mind.
You'll buy lunch for us?
No, you. Okay.
Buy lunch for us? Yeah.
Okay, so let me see. This is the abstract of the work. So as you can see, they deal with the separatrix. There's the critical value. So the cell force, and they are interested. That's what they can do with the computations and the analytical calculations. Is that okay? That part is what is known that I showed you before. Is the logarithmic divergence of the separatrix, but they want to find what happens when you take into account the cell force contribution, so something that will be corrected by this parameter. So they find that this correction, it's a kind of a paradox because it's a stronger divergence, which has when B goes to BC. It's 1 over B, and this is a stronger divergence than the probability. So therefore also the result is the one that diverges. The first term is the one that I showed you before, B minus C, and here comes the one self contribution. So BC of B minus BC. Okay. So, and they even define a non-trivial result. This is result, it's found by numerical. As I told you, it's a hybrid procedure. They mix analytical computations with numerical, very heavy numerical computations. So at the end, they find that the equation for this, combining the tools, so it's a parabolic behavior. Okay. And they have a sort of a derivation for this. Okay. So as I told you, it's a mixture. So that's what they can say about the separatrix. How is it affected by the self-force effect? And at some point, they mentioned that this sort of result can be cast in a unique formula as self-force. So you have the logarithmic, and this term is, it's the derivative of the logarithmic function. So this is a kind of Taylor expansion. So this is the leading term, and this is the subleading term. So they mention at some point that this can be found by putting something like a first correction here. Okay. So it can be rewritten in such a way. So this is the result, that the separatrix has a first order correction in the equation of the separatrix. Okay, so I'll try to say things that in half an hour I can explain. No, okay, so that's the part of the results. They have many other results that I'm not mentioning, but that's the one that I'm interested in. Okay, it's a nice result, but it's only something that is studied asymptotically. They don't have the equation for the separatrix in an ordinary situation where the impact parameter is not necessarily close to the critical parameter. But okay, that's a result, and it's a non-trivial thing to find this. Okay, the sort of result that they found, it's what one calls the one self-force contribution, but this computation here considers any order of perturbation in G or in relativistic sense, so all order, all PM order, for example. So it's a strong result. They don't have any explanation for this result. It would be very useful if some theory behind, strong theory could explain that result, but okay, they don't have this. Okay, so let me see. The thing is that using the EOP 31 body framework, we succeed in explaining these sort of things, right? Why? In fact, this comes from a behavior like this. Okay, so since I don't have time, let me be very selective.
So in this framework, you recover these numbers there?
No. That's it. Okay. So that's what I was telling you before. Oh, those are with self-corrections that we. So as I was telling you, for example, the one on the top is the one with which is Schwarzschild. And the other ones which include 2 p.m. self-force corrections, 3 p.m. and so on, are the ones which incorporate the self-force effect, right? But those are 2 p.m., 3 p.m. It's always an order of approximation, right? So one hopes that this converges. So these are, in this sense, these sort of results are more modest because what they found is an all PM order to every order, and what we do found it's up to here in these computations up to 3 PM order. But okay, we can justify this this result. We can justify because already at 2 PM, 3 PM, these things begin to arise. So it is fairly easy to see that if you add all the contributions, it will always appear like this. Okay, so maybe, no, I think those are the graphs. Okay, the one on top is the Schwarzschild one, and the other ones are 2 p.m., 3 p.m. Okay, so what can I tell you? This is for those graphs, one can study the behavior for lower energies, and lower energies mean energies close to 1. So there's this value 4, right? The 4 GM that I mentioned before. So when energy tends to be the minimum value, it agrees with the value in Schwarzschild. At least this is the 2 p.m. Okay, when one does the 3 p.m., okay, more elaborated situation comes, but you make this energy go to 1, so the second and third line become 0. What one sees here is that it's no longer 4, has the self-force correctness. Okay, so that's why I think you should believe me that they have a small gap, right? And this is for high energies. And what is important is that for enough high energy, it's very different from it's straight line, okay, but it's very different from the one from Schwarzschild. So this is why you see Schwarzschild as this angular coefficient 3 square over 3. That's the leading term. And when okay, maybe this point, I'm sorry. I'm really sorry. Maybe this point should be stressed. When you do the 2 p.m. contribution, you find that the leading term is not exactly the same angular coefficient. It's a little bit lower. And what is remarkable is that this result does not depend, this leading term does not depend on the value of nu, right? As long as you turn on a little value of nu, from that situation, you come to this other situation. The new corrections come here in the subleading and so on. And this also happens when you take into account 3 p.m. contributions. The computations are harder, but you have now the coefficient is a bit less. Okay, so maybe I should go to the final remarks. Okay, so a general remark is that I didn't have the time to explain you, but in order to do these calculations, what one uses is the effective one-body framework due to Zamor, Bonanno, and recent results, and a different version, a complementary version by him into 2017. And the technical remarks is that, okay, we can explain that situation that I've observed in the Barak-Long-Whittle model for the separatrix, that behavior from, okay, I didn't have the time to show you, but it's fairly easy to see. The technical remarks, there are nice things about our calculations. Okay, the calculation that we do can work in that scheme of a toy model, but what is our main interest is that they can be done for general relativity. So if it can be done for general relativity, okay, you say what we learned so far is very good, but these are the calculations that we need to do. So in these computations, consider as well radiative as well as conservative, which is something that didn't happen in the modern term because they have a spatial fix, so they only have radiative corrections. And as I told you, we do have an equation for the separatrix. We use that equation in those plots, which is much stronger than simply having the asymptotic behavior. This is one aspect, right? But we do have the equation for the separatrix, which is something much stronger than that. Okay, we have an expression for the scattering angle. There you can find the situation. And what I told you, we have a justification for this. The justification goes along these lines. But you can see in the computations how this arises. Okay. And what I was telling you, what you can get of all this. The main conclusion is that impact parameter is lower if you compare the sulfur situation with the Schwarzschild situation. But if you consider as was a very high energetic situation when velocities are of the order of the speed of light, okay, what you find is that the leading term that I was told you is universal. Universal in the sense that it doesn't depend on the value of nu. It's something that doesn't depend on it. You should only tell him if nu is nu 0 or not. If it's different than 0, so you abruptly arrive to this situation. Okay, so the future prospect is to compare these sort of calculations with also numerical simulations done in the past. In those days, the people were worried about what happened in the LHC, if there were going to be some black holes or things like this. So they have some relativistic black hole collisions and some results, and they do worry of for which value of the impact parameters the merger happens, which is exactly what we are working at this point. Okay, so thank you.
Yeah, silly technical question. You're saying that you're resumming these two terms and that one is the derivative of the other. That actually should imply a specific relationship between A1 and A0.
Yes.
Do you have this one?
Yes, in our case, we do have it.
All right, so it's a miracle in a sense.
There or ours.
I don't know which one, but the fact that you can resum it explicitly like that is
yes. In our case, we do have an expression.
That should help understanding this bizarre form for A1.
Yes, but you should be careful that our result is only 2 p.m., 3 p.m.
Yeah, sure, but already at the very first order, I mean,
you can see
the definition of A1. I mean, A1, if you want to be able to resum everything like that, A1 should be defined in such a way. I mean, it has to be a function of A0 such that.
Exactly. Yes.
Well, this is a fit, right?
This is a fit. In their case, it's a fit.
There's no physical reason for this expansion.
Well, it should be then, because otherwise, at the end of the day, you still end up with a logarithmic divergence. It's just that you're shifting the place the divergence occurs. Yes. So physically speaking, there should be an actual reason why to be able to calculate this A1.
Yeah, but why stop at the V square, at the V cube?
They have no answer for that.
You need to put more in there.
It's just a fit.
It's just a fit.
More questions? Okay. So
everybody's hungry.
So let's say Ricardo. Reconvene at 2 p.m. for the third block of the day.
Yeah.
2 p.m. or 2 Paulo, maybe 2 p.m. Yeah, that's not those are higher orders. You can leave your stuff here.